All right, welcome. Today, we're pulling back the curtain on this, well, invisible world that's secretly running pretty much everything around us. Yeah, I'm talking about from the massive weather patterns that sweep across the globe all the way down to the cup of coffee sitting on your desk. It's all governed by the principles of fluid mechanics. So, let's just dive right in.
So I want you to just think about this for a second. You've got a massive steel ship, right? A passenger jet soaring thousands of feet up in the air, and the actual lifeblood that's pumping through your body. I mean, they seem totally unrelated, don't they? But they are all ruled by the exact same set of physical laws.
And the answer is fluids. That's the one thing that connects them all. Now, when I say fluid, it's not just, something you drink. In physics, a fluid is basically anything that can flow. So that includes all the liquids we know, like water and oil, but it also includes all gases, like the very air we're breathing. They are the heroes of our story today.
Okay, so to really get a handle on this fluid world, we first have to learn the basic rules of the game. Let's kick things off with two of the most fundamental properties that every single fluid has.
First up is density. To put it simply, this is really just how much stuff is packed into a certain amount of space. So imagine you've got a box of feathers and a box of rocks, and they're both the exact same size. Well, that box of rocks is way, way denser. This idea is absolutely crucial if you want to understand why some things float and other things sink.
Next up is pressure. And we've all felt this, right? The pressure of the air around us, or that feeling of the water pushing on you when you dive deep into a pool. It's the force a fluid pushes with on any surface. A good way to think about it is like this. The force from a flat shoe gets all spread out, so the pressure is pretty low. But that very same force coming from a high heel, it's concentrated on one tiny little point, creating a ton of pressure. Well, fluids work the same way, pushing on everything inside them.
All right, now that we've got the basics down, let's take a look at what happens when fluids are just sitting still. This branch of the science is called fluid statics, and believe me, it has some incredibly powerful rules. So first on our list is Pascal's law, and this is just a beautifully simple but incredibly powerful idea. It basically means if you squeeze a sealed container of water, like say a water bottle with the cap on tight, the pressure you apply in that one spot instantly spreads out equally everywhere inside that bottle. This is the exact principle that makes hydraulic systems work, like the brakes in your car. And that brings us to one of the most famous aha moments in the history of science. The ancient Greek thinker Archimedes, he was given a task to figure out if a king's crown was made of pure gold. And the story goes that as he stepped into his bath, he watched the water level rise, and he just had this sudden flash of insight. He allegedly ran right out into the streets, shouting Eureka, because he had just figured out the principle of buoyancy. And what he discovered gives us these really clear rules for why things float or sink. It's basically a battle of densities. If an object is denser than the fluid it's in, like a rock in water, it sinks. Simple. If it's less dense, like a log in water, it floats. And if their densities are perfectly matched, it just kind of hangs there, suspended in the middle. This is exactly how those gigantic steel ships, which are mostly hollow space inside and have a low average density, can float so easily on the water.
So far, everything we've talked about has been about still, calm fluids. But what happens when they start to move? Well, that's when the rulebook kind of gets a rewrite. We're shifting from the world of statics, which is all about pressure and buoyancy, to the world of dynamics, which is all about things like flow rate and the conservation of energy.
So, welcome to the world of fluid dynamics. I gotta say, this is where things get really, really cool. We're now talking about decoding the secrets of flow, the stuff that explains everything from how a river carves a canyon to how a jet engine works. Now, to make any sense of the potential chaos of moving fluids, scientists often start by imagining a perfect, ideal situation. They call it steady flow. All this means is that the fluid is moving smoothly, predictably. Think of a gently flowing river, not some raging, chaotic rapid. It's the perfect, clean laboratory for figuring out the rules. And the very first rule of flow is something called the continuity equation. And honestly, this is super intuitive. If you've ever put your thumb over the end of a running garden hose, you've seen this happen. The amount of water coming through that hose has to stay constant, right? So when you make the opening smaller, the water has no choice but to speed up to get out. It's really that simple. Smaller area means higher speed. And now we get to the absolute superstar of fluid dynamics, Bernoulli's equation. The key thing to get here is this relationship that feels kind of backward at first. So the continuity equation told us that fluid speeds up when it goes through a narrow space. Bernoulli's principle adds the next critical piece. Wherever that speed is high, the pressure is low. And where the speed is low, the pressure is high. This one idea is the key that unlocks some of the greatest achievements in technology.
Okay, so let's pull all these ideas out of the textbook and see how they play out in the real world. How does all this theory actually work, and what are the things that make it a little more complicated in real life?
A perfect, direct application of Bernoulli's principle is something called the Venturi effect. This is what happens when you force a fluid through a narrow, constricted section of a pipe, sometimes called a choke. So, as the space gets smaller, the fluid speeds up. That's our continuity equation. And because it speeds up, its pressure drops. And that's Bernoulli's principle. This effect is used in everything from the carburetors in old cars to paint sprayers.
And seriously, the applications are just everywhere. There's Torricelli's law, which uses it to figure out how fast water will drain from a tank. In medicine, Doppler flow photometry uses these same principles to measure the speed of your blood. And probably the most famous one, airplane lift. The wing is shaped so that the air has to travel faster over the top. Faster air means lower pressure on top compared to the bottom. So the higher pressure below pushes the wing and the whole plane up. Even the heat pump in your home is playing by these rules.
But of course, the real world always has a catch. And in fluids, that catch is friction. We have a special name for it, viscosity. It's just a measure of how thick a fluid is or how much it resists flowing. Water, for instance, has really low viscosity. It flows super easily. Honey, on the other hand, has very high viscosity. It flows very, very slowly. All of those perfect equations we talked about have to be adjusted to account for this real-world stickiness. Now, when the conditions are just right, when a fluid isn't too viscous and it isn't moving too fast, we get this beautiful, orderly state called laminar flow. You can actually see this sometimes, like in a smooth stream of smoke rising up, or when you slowly, carefully open a faucet. The fluid moves in these elegant parallel layers. But if you push it too hard or if things change, that smooth flow can break apart into the chaos we call turbulence, which is a whole other much more complex story for another day. So from buoyancy all the way to Bernoulli, we've seen how just a few key principles of fluid mechanics really do dictate how things float, fly, and flow. The big takeaway here is that these aren't just equations in a book. They are invisible forces that are actively shaping our world, every single moment of every day. So the next time you see a bird catch an updraft, or you stir your coffee, or just watch the clouds drift by, ask yourself, okay, where are those invisible forces at work right here? Thanks for joining me.